Now I want to go ahead and try solving some linear inequalities. So we can take steps to solve linear inequalities. Step 1, we want to solve each inequality, or simplify each side separately. I just tripped over all my words terribly. Apologize. Use the distributive property as needed. So we want to clear parentheses, clear fractions or decimals, and combine like terms. Step 2, we want to isolate the variable terms on one side. We use the addition property of inequality so that all terms with variables are on one side of the inequality and all constants are on the other side. Then we want to isolate the variable. So we're going to use the multiplication property of inequality to obtain an inequality in one of the following forms, where k is a constant. So we're going to have our variable either less than k, our variable less than or equal to k, our variable greater than k, or our variable greater than or equal to k. And remember, reverse the direction of the inequality symbol only when multiplying or dividing each side of an inequality by a negative number. Key thing to remember. So now we have our steps. Our steps are a little simplified in this case as opposed to our previous 6 steps that we normally do with applied problems. But on to our first example. We want to solve the inequality and plot the solution set on a number line. So at the very end, we have our number line and we're just going to fill it in with whatever our solution is going to be. We have the equation 5 times k minus 3 minus 7 is greater than or equal to 4 times k minus 3 plus 9. So we want to solve this the way we would solve any other problem. We just now have a different inequality sign as opposed to an equality sign. So we're going to go ahead and clear out our parentheses. So we want to distribute our 5 in this case. So we're going to have 5 times k minus 5 times 3 minus 7k. And we're saying that this is equal to 4 times k, using our distributive property, minus 4 times 3 plus 9. And I want to simplify a bit. So 5 times k is just going to be 5k. 5 times 3 is going to be 15. Minus 7k is greater than or equal to 4 times k is 4k, minus 4 times 3, which is 12, plus 9. We can simplify further. 5k minus 7k is going to give us negative 2k minus 15. We're saying this is greater than or equal to 4k minus 12 plus 9. So we know that this plus is like saying, or this minus is like saying plus negative. So negative 12 plus 9 is going to give us negative 3. So we have 4k minus 3. So we've simplified each side of our equation now, or each side of our inequality. And so now we can go ahead and separate out our constant terms and our variable terms. Let's go ahead and add 15 to both sides. So give us negative 2k minus 15 plus 15 greater than or equal to 4k minus 3 plus 15. And this is our addition property of inequality. So simplifying this, we get negative 2k is greater than or equal to 4k minus 3 plus 15. And remember, minus 3 is like saying plus negative 3. So negative 3 plus 15 is going to give us positive 12. And now we want to put all of our variable terms to one side. So we can go ahead, we're going to subtract 4k from both sides. So we're going to have negative 2k minus 4k is greater than or equal to 4k plus 12 minus 4k. And this is still, once again, we're just using our addition property of inequality. So negative 2k minus 4k is going to give us negative 6k, which we're saying is greater than or equal to now 12. So now we have a negative 6k is greater than or equal to 12. We want to isolate k, so we need to get rid of our negative 6. And the way to do that would be to divide by negative 6. And so we see we are dividing each side by a negative number in our multiplication property of inequality. Which now tells us that our sign has to flip. 12 divided by negative 6 is going to give us a negative 2. And we divided by that negative number, so our sign, instead of being greater than or equal to, is now going to become less than or equal to. We're going to highlight that. So now we have that k is less than or equal to negative 2. So if we put this in our set builder notation, so set builder notation, this is going to give us k, where now k is less than or equal to negative 2. And in interval notation, less than negative 2 means negative infinity to negative 2. And our negative 2 is included, so we give it a square bracket. And now we want to plot this on our number line. We're going to bring our number line up a bit here. So let's go ahead and start making some values. Let's just say that this value all the way at the end here is going to be 0. So this is negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, and negative 10. Let's go with, we'll do blue again. Let's do blue. So we have a square bracket at negative 2, which means that on our number line, we will also have a square bracket. And we want it again to be including values less than negative 2. So we're going to face it in this direction. Then we want to include values less than negative 2. So we're including these negative 3, negative 4, negative 5, all the way to negative infinity. So we color in the rest of our number line to the left. So there we go. That would be how we would solve for an inequality, especially when dividing or multiplying by a negative number. Now, objective 5, we want to solve applied problems using inequalities. So now we're going to do some applied problems. So it's important to understand the different phrases used to represent different inequalities. So a chart here that tells us different phrases. We have is greater than, a number is greater than 4, that inequality is x greater than 4 with our little symbol. I realize that by me saying them, it all sounds the same, but when you read them, you'll see kind of the difference here. So we have is less than, we have a number is less than negative 12, so we have x is less than negative 12. Another thing we say is something like exceeds. A number exceeds 3.5, and that tells us that x is going to be greater than 3.5. Exceeding, meaning we are going further, we are successing, we are moving in a positive direction, x is greater than 3.5. Then we have is at least. So a number is at least 6. So this tells us that x can be 6 or it can be greater than 6. So we have x is greater than or equal to 6. Then we have is at most. So a number is at most 8. This means that x can be 8 or anything less than 8. So we have x is less than or equal to 8. Word of caution, do not confuse statements such as 5 is more than a number with the phrase 5 more than a number. The first of these is expressed as 5 is greater than x, while the second is expressed as x plus 5 or 5 plus x. So remember that key difference there. 5 is more than a number. We have 5 greater than x, and if we have x plus 5, that means 5 more than a number. So it's really going to be that is, the word is in there is really changing that difference between our inequality and just an expression. So in our next example, we're going to be calculating an average. And in general, to find the average of n numbers, we add the numbers together and divide by n, which is our total number of numbers. So if you want to find the average of, say, 3 and 5, you add 3 and 5 and you divide by 2. You had the numbers 3 and 5, so there were 2 numbers, so you divide their sum by the number of numbers. So here we go, example 2. We have that Susie has scores of 84, 86, and 76 out of a possible 100 on each of her first 3 tests in history class. If she wants an average of at least 80 after the 4th test, what are the possible scores she can make on that test? So we have an applied problem. Let's go ahead and use our 6 steps as we normally would. So step 1. We read the problem. We want to know, what do we want? We want the possible scores Susie needs to get to have an average of 80. So by the wording of this question, we know that there's multiple solutions. We're going to have multiple ways that we can have an average of 80. So in step 2, we want to define our variable. And then in this case, our variable, we're going to let this be x, and we're going to say that x is Susie's score on the 4th test. So this is our variable. Our unknown is what she's going to get on her 4th test. Then step 3, we want to set up our equation. And in our equation, what we really want here to happen is that we want our average to be greater than or equal to 80. We're saying that we want at least an 80, which means that we would love anything greater than an 80, but an 80 is also acceptable. So we want our average to be greater than or equal to 80. So really what this is going to turn into is our average would be our first score plus our second score plus our third score plus our 4th score. And this is all going to be divided by our number of tests. So our number of tests. And we want this greater than or equal to 80. So taking the concept of what this average is, and we know the values of our first score, our second score, and our third score, what we don't know is that 4th score. And we know that there's 4 tests in all. So this is going to become 84 plus 86 plus 76 plus x in our numerator. And our number of tests is 4. We have 4 tests, and we want this to be greater than 80. And this here, remember, this whole section here, this is our average. So this is our equation that we're working with. And step 4, we want to solve this equation. So we want to solve 84 plus 86 plus 76 plus x, all divided by 4, greater than or equal to 80. So we want to simplify. Simplifying our numerator, we add the values of 84, 86, and 76, which is going to give us 246 plus x. And this is all divided by 4. Now remember, we want to isolate x as much as possible, so we need to get rid of our 4 in our denominator. So we can go ahead and multiply each side by 4. So now, since we multiply each side by 4, we're going to have 4 times 246 plus x divided by 4 is greater than or equal to 80 times 4, which is 320. And since we have 4 in our numerator and our denominator, this will simplify to just 246 plus x is greater than or equal to 320. And now the last thing that we have to do to isolate x would be to subtract 246 from both sides. So we're going to have 246 plus x minus 246 is greater than or equal to 320 minus 246. So now we get x is greater than or equal to 320 minus 246, which is going to give us 74. So now we're saying that Susie's going to need a 24 on her test. So we're going to say step 5. Susie needs to get a 74 or higher on her 4th test to have an average of at least 80. And our step 6 is going to go right off to the side here. So step 5, we've stated our answer, and step 6, we check. Just want to check and make sure that this is correct. So when we check our answer, we want to check and make sure that our value is going to give us at least 80. So we're saying that 86 plus 76 plus, 84 plus 86 plus 76 plus 74, all divided by 4, is going to be greater than or equal to 80. This is what we're stating. And when we add these values together, 84 plus 86 plus 76 plus 74, this is going to give us 320 divided by 4, which is greater than or equal to 80. 320 divided by 4 is 80. And since we have greater than or equal to, this statement is correct. 74 is our boundary. It's our lowest limit. But another way that we can check and that we want to check is we want to make sure that a value greater than 74 will give us an average of greater than 80. So let's say, and here we check that x was equal to 74. Now let's say that x is equal to 78. And if we do this and we say 84 plus 86 plus 76 plus 74, all divided by 4, we want to say is greater than or equal to 80. Well, when we add these values together, we're going to get 324 divided by 4, which we're stating is greater than or equal to 80. When we divide 324 by 4, this gives us 81, which is in fact greater than or equal to 80. So we've checked, and so now we know that our solution is that Susie needs to get a 74 or higher on her fourth test to have an average of at least 80. Writing this in our set builder, so set builder notation and our interval notation gives us x, where x has to be greater than or equal to 74. And our interval notation we have that we want 74 included, so our square bracket, to infinity. Technically we say infinity, but if our tests are out of 100, then this means that we would only consider values from 74 to 100. If 100 was the absolute max and Susie could get a 100, we would include 100 with a square bracket. So we're considering the interval from 74 to 100. The 100 makes our answer realistic in the form of our problem, but we could definitely write infinity if we wanted to. But we know that Susie couldn't get something like 1,000% on her test, so it's a little unrealistic for the application of the problem, but you could say that as well.